Hey guys, so today we're going to be working with potential energy of a system of charges, okay? Right around here, this big old title, okay? So let's imagine that we have four fixed charges, which is the square right over here, okay? So this is charge 1, charge 2, 3, and 4, okay? They each have their own charge, and they are separated by their corresponding distances, which, since it's a square, 10 meters for each side, so they're all separated by 10 meters, okay? So if I were to move a charge, let's say this one over here, okay, from where it is to over here, okay, how much work would I do in moving it there? And how much work would the electric field do in that movement? Okay, so to do this, we work with the concept of potential energy. Now, I know this concept can sometimes be very confusing for some of you, but let's find a very simple way of working with this by comparing it to a concept that is well known by all. Gravity, okay? So let's say that we have a soccer ball, okay, right over here. And I go ahead and kick it as hard as I can, So it's going upwards, okay, with all of the force that I put into kicking that soccer ball, okay? So let's say I transfer, I'm a professional soccer player. I transfer 500 joules of energy into the ball, okay? And because this is the ground, from where I kicked it, it had zero initial potential energy, okay? And now I go ahead and transfer all of those 500 joules, and it ends up with precisely those 500 joules of energy, okay? So what we did there was that the work that I did is equal to the final potential energy, okay? So the work, my bad. So the work that I did, I'm just gonna go ahead and write an I. Okay, that is equal to the final potential energy. So I'm gonna write, there we go, minus the initial potential energy that it already had. And initial. Okay, so since it had, zero initial potential energy, we're left with 500 joules, which is what I transferred, minus 0. Well, that's left with 500 joules of potential energy. Okay? Now, going on with the electric field, it is the opposite, actually. So this is how we get how much work I did, okay? Now, if we want to also see how much work the electric field did, it's just the opposite of that, okay? So let me go ahead and make a little bit of space over here. Let me move this just a little bit. Okay. So going back to our example of the soccer ball, while I'm kicking the ball and it's going upward, gravity is applying work downwards in the opposite direction. And, well, that's what electric fields do. Because if gravity wasn't applying a force downward, well, the ball would go all the way to the moon and it would never come back, That's why when we jump, we fall back down, Gravity is always, applying a force onto ourselves, onto anything that we do or something of the sort, okay? So the work done by electric fields is initial potential energy, okay? So the work done by electric fields, okay, so it's equal to initial potential energy, okay, and then minus final potential energy, okay, oops, my bad, there we go, minus final potential energy, okay, so it applies negative, because we have here 0 at 500, so it applies negative 500 joules, okay, of potential energy. Forgot. There we go. Okay. So, this is very important, these two formulas right over here, which is the work of electric fields is initial minus final, okay? And the work that I did, okay, is final minus initial, okay? So it is very important that you don't get those two mixed up, okay? So just keep them in mind, and we're going to be working with them very soon, okay? So basically what we need to do now is figure out the initial potential energy of our square, which once again is this right over here, and the final potential energy of the square, and we can figure out the work. Okay, so once again, this is the initial potential energy square, and let me go ahead and draw what the final potential energy square looks like. Okay, I'm gonna write down over here that I did is equal to final minus initial. Okay. All right. So let me go ahead and draw the final square. Just a crude little drawing. Oops. There we go. And let me actually move this just a little bit right over here. Okay, and this one goes inwards. Okay. Oops. So we have a line going from here to here, here to here, here to here, and there to there. Okay. Really ugly drawing, but you guys get the point, don't you? So this new distance is 5 meters, 5 meters, 10 meters, and 10 meters, okay? And this is -5 coulombs, 3 coulombs, 2 coulombs, and 5 coulombs, okay? So this right here is the final potential energy. It's the modified square, if you could, that's what we're talking about, okay? So the way in which we calculate the potential energy for a system of charges when there are more than two is we go by pairs, okay? So the formula, let me go ahead and write that down, is U is equal to K, which is a constant, okay? The electric constant, you already know, 9 times 10 to the 9th. And then we've got Q1 and Q2, okay, over R12. Okay, so Q1 and Q2 are the two charges of the pair, and R12 is the distance between those two charges. Okay, so what we're gonna go ahead and do right now is let's get started. So we have the first one over here. That's gonna be 5 coulombs. Okay, and then that's gonna be times 3, because that's charge number 2 right over here, okay? And then the distance is 10. Okay? So that would be U is equal to 15 over 10. Well, that's just 1.5. So 1.5. We're going to leave it in terms of K, just so we don't get that much into it, but you guys get an idea of what we're working with, okay? So let me go ahead and erase this. And let's work out each one. Okay, so I'm just going to do these just a little bit quicker, okay? So this is the same, 5, 3, and 3, -5. So that's going to be -1.5 K. Okay, next we got -5 and 2. Okay, -5 and 2, so that's -10. Over 5, well, that would be -2. Also in terms of K. And the next one is also the same, 2 and 5, so that's 10. Divided by 5, that's 2. oops. Okay, so that would be 2K. Okay? And what we do in the end, okay, is that we just simply add them up. Okay? So we have here, okay, so let's go ahead and do this. We have 1.5 minus 1.5, and then 2 minus 2. Okay, and what we are left with is a total potential energy of 0, okay? So that's the final. Okay? And now let's go ahead and move on to the initial potential energy, okay? These charges are going to be of, final potential minus final initial, okay? So let's go ahead and work this out. I'm going to go ahead and erase this. All right. So now let's go ahead and work with this, okay? All right, so let's go ahead and get started. We have the first 5 and 3, so that's 15. And then we would get 1.5 once again. All in terms of K, by the way. Okay, then we get, once again, negative 1.5. Now, negative 5 times 2, that would be negative 10. Over 10, that would be negative 1. And then 2 and 5, that would be 10. Okay. Over 10, that would be 1. Okay. So what we do have here, okay, is 1.5 and negative 1.5, that's 0. And negative 1 and 1, that's also 0. Okay. So now give me just 1 second. Okay. So, this is a, kind of a strange case that we're currently working with. I wanted to present it to you guys just so that you guys know that there are sometimes strange cases in which this can happen. Okay. But don't worry, you guys do definitely get the idea of how this works, So what we would do here is we're going to go with final potential minus final initial. Final potential energy minus final initial potential energy, okay? So, this is just one weird case in which we have, 0 minus 0. So that would mean that this is the change in potential energy, okay? Which is the work done by me and the work done by the electric field is opposite. So in this case, if we would have been left with, 5, so we just change it over to negative 5, because this gives us a change in potential energy, which is done by me, okay? The work done by me. And the work done by the electric field is the opposite, so we would just go ahead and change the sign, okay? So, yeah, that's pretty much it, guys. I do hope that you guys didn't get too confused over here at the end. Please do leave a like and support our channel. And, leave any recommendations on how we can improve or how we can make better videos in general. But yeah, I do hope that you guys enjoyed it. Have a great day.